here we go. So this is just kind of some random notes. I want to first talk about springs, and then after I've talked about springs, we'll kind of talk about mechanical energy and like conservation and like open closed systems a little bit. So for springs, let's just write a little bit about springs. Springs. So for springs, there really are honestly only two equations. And this, I'm going to write it the way that it's on your AP equation sheet. Force for a spring, which has a direction. Forces have a direction, so it needs a little hat over it, little vector thing. Vector just means something has a direction, is equal to the spring constant, which is how strong the thing is, times how far it has been stretched or compressed. And so we see here there's an absolute value bar on the x, because if it's compressed, maybe that's a negative distance. If it's stretched, maybe that's a positive distance. It doesn't matter. We're just going to take the absolute value, make it a positive, right? So K is just the spring constant. That's really just a measure of its strength. That's really all it is. Like, you ever drive a car, you ever sit in a car, you go over a bump, you feel the car kind of bounces a little bit. Those have mighty spring constants in the shocks in your car. If you ever see like a lifted truck, right? They have this giant, huge freaking coiled spring that is literally their shocks, like their suspension system. And so they just have a giant spring constant. They have a very large value, like thousands of newtons per meter squared. The other one is x, which we just call is the distance stretched or compressed. So that's really it. Distance stretched / compressed. All right, that's it. Springs are pretty simple in that regards. Now, where it got a little wonky is I suddenly like gave this new equation, US, and it's like potential energy, that's U, and S denotes its first spring, is equal to 1/2 kx squared. Well, the nice thing here is you only have to learn this new symbol. US means the energy stored in a spring. That's really it. That's all there is kind of to that one, at least. The hard thing is going, well, where the heck did this come from? Well, you have two options, in all honesty. You could totally like learn this derivation. You don't have to learn the derivation. If you can just find both of these on your equation sheet, you're golden. That's really it. That's all there is to it. I'm not expecting that you know how to go from this equation and derive and like come up with this next one on your own. Like that's not what I'm expecting. I do expect that you understand that U means potential energy and US is spring potential energy. That's really what I do expect of you. Potential energy. Okay, sweet. So what this really boils down to and means is that maybe I have a wall here, and attached to the wall, and maybe we go, let's put some ground on us here. There we go, and whomp. Okay. So now I have, let's say, a spring, and there. Let's say that this spot is equilibrium. Equilibrium is like when it's relaxed. You're not pushing on it, you're not pulling on it, nothing like that. So this is equilibrium. Well, this is when x is 0. Well, the distance it's stretched or compressed, it hasn't been stretched or compressed. So x is 0. If x is 0, that means there is 0 force the spring is applying. There's no force that it's acting with in either direction, right? And also, if x is 0, well, that means there's no energy stored in it. And so the cool thing is, if, I don't know, you had some box, let's do a blue box right here. If I had this blue box, no matter what's actually happening here, my blue box or the spring here has 0 energy stored in it. Now, that is true even in the scenario where my spring, let me see if I can grab my spring. Let's say my spring was like stretched way the heck out here. All right. And let's say that my box was stuck to it. So my box is here. My spring was pulled way the heck out here. We'll call this distance x stretch. I'm just making up a distance here. It doesn't really matter. Well, that means obviously the spring is going to be acting and pulling to the left with this spring force, right? Like that's kind of what that means. The spring is going to pull back towards equilibrium, right? And so let's say right here, this is the maximum distance it gets, this max X stretch. We could even call it X max or something instead. Well, since it's the maximum X distance, we're gonna have the maximum amount of energy stored in this spring, is what this really means, right? And so what happens then is eventually the spring and the box start moving and moving and moving. And as the spring gets closer to equilibrium, this X thing diminishes, right? Well, if X gets smaller, that means the force it's applying gets smaller, right? Which is kind of odd. It actually gets weaker and weaker the closer it gets to this equilibrium point in red. And also, as X goes down, well, the spring stores less and less and less and less energy. So my question then is, where the heck does the energy go? Because we've talked about energy in class and gone, well, like we don't really get rid of energy. It doesn't just like poof disappear, right? It has to go somewhere. Well, in the case of this, the spring would be making the box go faster, right? This spring potential energy would be like becoming kinetic energy of the box, right? Until the spring and the box end up reaching literally equilibrium, right? So I'm not saying that they suddenly stop though. If you try to play out kind of a picture or a little movie of this in your head, the box was over here. Well, the whole system of the box and the spring is going to move to the left, and it's not just going to suddenly stop here. It's going to keep cruising by until it reaches some new maximum compressed distance. And then it's going to go back, and then it's going to go back again, and it's going to kind of oscillate would be the fancy term we could say. It's kind of going to bounce back and forth like a spring does. It goes back and forth, and maybe it gets closer and closer and closer and closer until it eventually stops. But the idea is that it's not actually just going to immediately stop at equilibrium. But the neat thing, while it's working its way until we get to this whatever, I don't know, X compress, is that right here, even though it's going to keep going to the left, since there's no energy stored in the spring anymore and the spring isn't applying any force, there is zero net force on the box. It's just moving with a speed, which is kind of crazy to think about. And there's no energy stored in it. So where the heck did all the energy go? Well, the energy is all kinetic energy right here. It is maximum kinetic energy is what's really happening here. It's all kinetic here. And as the box starts creeping to the left, well, we suddenly start having more energy goes back into the spring until the box stops here. And then the box stops here, and now we're all potential again. And then it starts cruising back towards equilibrium, and now this potential goes away and it starts becoming kinetic again. So that's kind of my little, I guess just kind of quick and dirty rundown on springs and spring potential energy. We could go through and derive like where the heck does this come from. I've already done that. I don't want to like spend time doing that again today. I want to talk about closed and open systems. So with that, let's kind of slide down a little bit because I have some here. So this first giant kind of wiggly thing in the blue and green, this was something you already have in notes. System is just like whatever the heck the objects you want to analyze are. The surroundings are just everything else. The surroundings are also sometimes called, AKA also known as the environment. It's like you go see like the Disney Channel or you're watching Nature Channel or something. It's like, oh, there's gorillas. The gorillas are in their natural environments, all the stuff that's surrounding them. So here's what I wanted to add a little bit. And if you're someone that was like, whoa, those multiple choice problems were super gnarly, what the heck? This might be the thing that's really worthwhile to put down on page 101 in your notebook. But it's that a closed system is this kind of system that does not allow transfer of energy or matter in or out. It's like a sealed box is the way I like to think of it. And more importantly, there are no external forces that act from outside on a closed system. Now, maybe that part seems random. If you think about it, and you had some system though, and you'll see this in a moment, an external force. Well, an external force, if we had a force and acted over some distance, it would be doing work then. Work would be changing the amount of energy inside the system. So essentially, no external forces is just a different way that we can say the energy is not changing. is kind of really what's happening here. Like the total mechanical energy, really, is what I would say. So it doesn't really allow transfer of, and I would even be more specific and say mechanical energy here. Now, if you're that person that's like, whoa, what the heck is mechanical energy again? Mechanical energy is just a combination of potential and kinetic. It doesn't have to be spring potential. It doesn't have to be gravitational potential. It could be both. It could be kind of a combination of them. So if that's a closed system, it just does not allow transfer of energy in or out. There's no external forces. Well, an open system is the opposite, quite frankly. It does allow energy to be taken or removed. That means that there are external forces that act on it. So let me just give an example. And I think seeing examples, you'll be like, oh, I get it. Like, okay, this is actually easier than he's making it sound. So there's a block released from rest on a frictionless track. All right, so here's my block. Here's my shoddy little kind of doodle. Is the block track system open or closed? Okay, well, it's frictionless. Okay, so there's no non-conservative stuff. There's no like friction that's like going to steal energy away. But it says the block track system. If we look at just the block and track system, and this is where it might be a little weird and where I'm going to kind of like stretch your thinking a little bit. If it's released from rest, that means the kinetic energy up here is 0. But since it's just the block track system, there is also no potential energy due to, and I think my computer is going to have to close this. Sometimes I write too much too fast. We'll see if it closes it or not. Yep, there we go. And let's come back. Okay, so I said that there's no potential energy, and you're probably like, what the heck, Johnston? You lied to us. I know it's up some height, right? It's up this height, h. What the heck, man? Well, it says the block track system. It doesn't say the block track earth system. Between this block and the earth, yes, there is potential energy. But since we're looking at just the block and the track, like this could be, I don't know, in deep space or something, right? Or really, it could be sitting on a table, but we're not taking the Earth into account in our system. Remember, a system is just what we're choosing to analyze. Now, in most cases, you're going to include the Earth in this. Like, I'll be frank with you. But in the case of this is in fact an open system. And the reason I say it's open now, and this is where hopefully kind of some of the dots start clicking and pieces start coming together, is because there is an external force. I said open, there are external forces that act. Since we're not including Earth here, there is this external force of gravity, and the block is in fact going to drop down some distance, right? So as it falls from here to here, it's going down some height, and there's a force acting on it. And so what's happening is, even though there's 0 energy in the beginning, when the block gets down here or even here, it's going to have an amount of energy greater than 0. So where the heck did it come from? Because closed would mean this amount stays the same. It can't stay at 0 if it's going faster through the loop. Well, it's because the Earth is an external, is an object applying an external force that is acting on it. And it's essentially, like, it literally is, it is adding energy. Sorry, this should not say taken or removed. This should say added or removed. The Earth is in fact adding energy to this system of the block and track. Okay, so let's look at another one to kind of hopefully click it a little more. There's a ball, it's released above the ground, and let's make it a little more specific. Let's even say released from rest. Okay, we'll go from rest. From rest. Well, what would be an open system and what would be a closed system here? Okay, well, maybe after the last one, you're already going, okay, well, a closed system definitely has to include the Earth. So an open system would just be, the ball. Because it's released from rest, that means it has no kinetic energy. And since it's just the ball, is what I'm looking at for like an open system, just the ball can't have potential energy with itself, right? Like, that's nonsense. If we're looking at just the ball, there is no potential energy. Now, if it's just the ball. So at the end, when it's like down here and it's like speeding up and it's going faster, it has literally had energy added to the system. Well, there's something outside that was acting on the system. So it must be a open system. We've had energy added to it, is what it's really saying. And so that would be just the ball. Now, a closed system, and hopefully this is kind of an easy one to kind of get the ball rolling, would be the ball and Earth. If you consider the ball and Earth, well, now it has some amount of potential energy that is not zero. It has some real amount. So it's all potential up at the top. So potential, it's all potential. And then when the ball's like down here at the bottom, well, then it's all kinetic and the potential is zero. Well, we just swapped those two. This would be a closed system. The amount of energy, so let's look again here. There has been no like transfer of energy in or out. So it has all stayed the same amount inside this system. In this case, if we consider the Earth, there is no other force outside that's acting to change the amount of energy here. And so this is kind of, I guess, like a great example of, oh, how do we just want to look at it? If the question's asking me to consider the ball and the Earth, well, heck yeah, that's closed. But some of these AP questions will say, what about the system of just the ball? Where it's actually a really easy question, but it's just checking to see, do you really get this difference between open and closed systems is really kind of all it's saying here. And now I want to maybe take this and do something weird with it. Let's see if we can do that. There we go. So now I have one like this, okay? And so this is kind of an interesting one because we now have height up here, and we have like potential energy due to gravity. We also have a spring though, so we'll have potential energy due to the spring, and this box is going to be moving. So we also do have kinetic, right? And so maybe there's some point where you kind of put the box up on here and you go, okay, like I got everything ready. So here's kind of my setup, right? And you go, all right, well, we're looking at this and we go, okay, well, here is our equilibrium point. Here's kind of where x equals 0, right? This would mean that there's no spring energy here. But then let's say you take your hand and you push down on the box. So you're going to take the box and you're going to like smush the box down, and the box shouldn't smush itself as well. It's just kind of how the computer works. But now you're going, okay, well, great. What the heck's going on here? Well, it went from up above to now like down here, right? So we could look at this, and depending on how you set it, the box may have different kinds of energy. Now, when I look at it here, I would probably go ahead and I would say that it does have some height. I would say it has some height from here all the way to here. So that means it does have potential energy. Like it totally does. I would say yes, next to potential energy due to gravity. Right here, I would say it's a no for spring energy. But now let's kind of look at my scenario where I squished it down again. Where I squished the thing down, well, now I have lost potential energy, right? So this one has gone down, but now we have gained spring energy, right? And I haven't let it go yet, so we could still have kind of a no here for no kinetic energy. And so really what I'm trying to really convey here is you have to be comfortable with going, okay, what kind of energies do we have? What's going on with them? And how would I represent them? And in the case of mine, I've been secretly including Earth in with this system. When I said yes, it does have potential energy, that's because I'm assuming we have the box, we have the spring, and we have the Earth. If I forget the Earth and it's not included, well, there's never going to be any potential energy due to gravity. But then there's this outside force that's out of the system because we know gravity's still there and it's acting on it, and it's going to be doing work then. And that kind of makes things a little trickier sometimes. So with